Okay. Thank you to the organizers for inviting me. This is actually going to be a LIGO, Virgo, or, well, as people say here, Virgo LIGO results talk. So I'm trying to connect this a little bit to the topic of the workshop, which is singularities. Hopefully there's some connection. So the motivation for building gravitational wave detectors, for looking at signals in gravitational waves is general relativity, but we know that general relativity cannot be a complete description of what's happening inside these objects that LIGO and Virgo have been observing. So at some point, general relativity stops being the correct description of these objects. Then you have to have something else. What is it? And in particular, does whatever resolves the singularity, does this have any effect that could possibly be observable? So there's many places you could look for deviations from general relativity, but one reason for looking in LIGO Virgo observations is, well, somehow we know that these bits of space-time which have horizons and inside which you need to resolve singularity, we know that they exist at particular locations. We know that they've been interacting very violently with very strong dynamical gravity at some point. So maybe this is a good chance for seeing some deviations from general relativity. Of course, in GR itself, all of the activity is hidden behind the horizon, but okay, you can't necessarily assume that GR holds, even to that extent, that everything is masked by the horizon. So for that reason, I've called the gravitational wave sources we've seen singularity workshops, meaning places where, well, whatever we call singularities or whatever resolves them, they may be formed, they may merge, they may even be destroyed, who knows? So it's like a building site or metal workshop for singularities. Okay, I think we know what gravitational waves are. I'm not going to explain further than we had two very nice lectures this morning telling us about the theory and how to predict the gravitational wave signal in general relativity. Einstein said his greatest mistake was to put in the cosmological constant to his equation, to his GR defining equation. It turns out this wasn't a mistake. So possibly his next greatest mistake was to say that gravitational waves emission must be vanishingly small in all possible cases because of this extremely small prefactor in the equation of motion for source of gravitational waves. Of course, he didn't know at that point that things like black holes and neutron stars with extremely compact, possibly extremely fast moving, that he didn't know that they existed. So it took people like Chandrasekhar a few decades later to point out that this was possible or even necessary. There's also a debate for some time about whether gravitational waves really existed or were physically meaningful or detectable. Well, it turns out if you can measure the distance between 2 points, you can measure a gravitational wave. What we do is not necessarily have a direct measurement of distance, but we have measurement of the time it takes pulse of light or a wavefront to go from one point to another point and back. So, well, round trip time. So this is similar to a distance measurement. It's a well-defined thing you could do in terms of the result is independent of the gauge, and it's basically if you can imagine setting up a Michelson interferometer here, you will get a non-zero signal out of it because the actual physical distances between points are changing. Okay, I will skip this. So as I said, the closest thing that we can observe to whatever we can think of as being a singularity, or whatever resolves the singularity in a theory beyond general relativity, closest we can get to that is a few kilometers in some coordinate distance. Because that's the size of the black hole horizon, it's the size of a neutron star. So for most of their lives, these astrophysical objects are not giving us any signals which would tell us about the metric in particular. It's only right at the end of their lives or right at the beginning of their lives in terms of black holes that you have sufficiently violent perturbations of that metric to give us signals that we could possibly see. So in particular, a neutron star binary is believed to create a black hole at the end of the process. So that's in some way getting close to a singularity. Core collapse supernova also creates a black hole, or should do. We haven't seen any such signals, but if we were to, then in some sense this would tell us about the formation of one of these singularity spacetimes. There's also, I don't know if I can play this movie. Oops, nope, I don't know. Well, this is a pulsar, so this is an isolated neutron star. So, there's sources of gravitational waves which are not just single events which may produce black holes or merge black holes. There's, let's say, quieter sources of gravitational waves which extend over possibly years, possibly millions of years. So that's another way of detecting a gravitational wave source. Again, this is not one that we've actually seen so far. So I'm going to say a little bit about the methods of detecting gravitational waves in reality. So in particular, even though we're looking at the most violent and strong gravitational wave sources in the universe, still the strain, the fractional changing length that we see here is order less than 10 to the minus 20. So that's still pretty small. I mean, people say smaller than the diameter of a proton, something like that. So how is this technologically possible? I mean, you can believe that it is, but it still needs decades of work, and it still needs a lot of explanation as to how you can see that it's really technologically feasible. So the basic idea, as I said, is just the Michelson interferometer. If you imagine just here the laser, beam splitter, two n-test masses, that's what it is. It's just a big scaled up version. And of course the photodiode to see the light and dark fringes. The extra parts are to amplify the signal that you would get with just the Michelson part. So specifically, before the beam splitter, we have a cavity called power recycling. So the laser, we need a very special laser which is incredibly stable in terms of the frequency, in terms of the amplitude. It's difficult to build that with an extremely high power as well. So what we do instead is we put a cavity here in which the laser power is amplified by a large factor before it even goes into the interferometer. Each of these arms is 4 kilometers long, and the light is effectively reflected by several hundred times in each one of the arms. So it's as if the light was traveling down not 4 kilometer arms, but thousands of kilometers of arms before it is allowed to recombine. So that also boosts the signal relative to just the simple Michelson. And okay, there's a whole load more of tricks and technical fixes that go into this, but it doesn't mean that we have to detect, let's say, 10 to the minus 23 meters in each of these n-test masses. It's a lot easier than that. It's maybe only like 10 to the minus 19 meters. This is obviously quite easy. So this is the physical realization of that. there's two LIGO sites, and I'm going to talk about Virgo as well in a minute. These are almost as far as possible from each other on the American continent. So one in Washington State, one in Louisiana. Well, as far as possible with the constraint that they should be built somewhere which is basically totally uninhabited and otherwise waste ground to make it easier to buy the land. They're 3,000 kilometers apart, so if gravitational waves travel at the speed of light, the longest it should take a gravitational wave to go from one to the other is 10 milliseconds. And it turns out that the gravitational wave detectors, you can't really see the orientation here, but they see almost the same gravitational wave signal, well, modulo a sign flip. One of them has its arms like that, the other one has its arms like that. So if you see the same signal at both of them within 10 milliseconds, you can be pretty sure it's a gravitational wave. So no, that's my explanation of data analysis. Well, okay, I have one or two more slides on the details of data analysis. It's taken since, let's say, about 2000, around 2000, the facilities, so enormously long, large vacuum systems and big chunks of concrete to put them on to keep them stable, those were built at these sites. It's taken, from then about 15 years to get to the level of astrophysical sensitivity where we're actually able to see a source. And no, this is some sort of encouragement that, well, okay, at least it's going to take maybe even longer, but no, you shouldn't give up just because it'll take a long time to get to your goals. So one way, as I said, in which you can enhance the sensitivity of the detector is to boost the signal. So long arms make the signal easy to detect. High power laser also increases the signal you get out. And one reason for using high power is basically we have lasers are made of photons, and to measure the difference in intensity, basically you measure the difference in the number of photons, but you have a counting error on that. So it's just quantum mechanics, and you call this shot noise, or you call this quantum noise, but you're limited by the number of photons that you can count, so you're limited by the amount of power you can get in the arms. So that's one reason to have this high power laser. Power recycling here before the light goes in is about a factor of 30, 35. Resonant arm cavities, a factor 300. Eventually, one wants to get the power in that up to 100 kilowatts. So that's actually, the radiation pressure eventually may actually be one element of the noise in the interferometers. So, okay, signal recycling is yet another stage here, which is actually to adjust or to optimize the dependence of the noise on frequency. So this is a typical, let's say, from the last few years, noise curve. So what does this mean? Well, this is almost as simple as just taking the Fourier transform of what we get out of the interferometer. So the strain measurement is strain as a function of time. Well, okay, the amplitude of the Fourier transform. So basically, you can see that at low frequencies, we have a lot high amplitude oscillations of strain. So this is mainly due to the fact that, well, low frequencies, everything wobbles. So this is, every part of LIGO is moving. And it's moving much more at low frequencies. You have seismic disturbance, you have anthropomorphic noise, what am I saying? Anthropogenic noise, so people walking about, trucks, trees falling in the wood. At high frequency, it's quantum noise. So essentially, the shorter a gravitational wave cycle is, the less photons you can be counting during that cycle. That's the hand-waving explanation. So the effect of quantum noise actually increases at high frequency. In the middle, you have this kind of sweet spot, which just happens to be where you see this class of astrophysical signals. Now, okay, already we have very rapidly rising noise at low frequencies, although we've part of a very big part of the design of LIGO is how to suppress seismic noise. So in particular, if you can imagine just a crane on top of that attached to the ground, so the end masses, so the end mirrors of the interferometer are suspended on top of 3 other sets of masses, and this is basically just for damping the vibrations that are transmitted from the top of this assembly to the ground, or from the ground to the top of this assembly. So just in order to be able to get a stable cavity between the 2 mirrors in each arm, you need to suppress these vibrations from the ground by at least 10 orders of magnitude. So that is these rapidly rising noises on the left: seismic noise, Newtonian noise, suspension noise. In fact, suspensions, LIGO is operating at room temperature, so there's also thermal noise in all of these. There's also some thermal noise causing all of these components to vibrate. So that rises at low frequency as well. The other main component, apart from quantum noise, is actually in order to make the mirrors reflect in the right way, you need to put coatings on them, and then coatings come with their own sets of noise. So because there's a junction between the mirrors, which are made of silica, and the coating, the fact that that junction exists produces thermal noise, and also there's thermal noise generated inside the coating itself. So that's actually limiting at mid frequencies. Okay, this is a projection for the final advanced LIGO sensitivity, which should occur, I guess, well, 2020, 21 or so. You notice this final sensitivity is 1, 2, 3, 4, a few times 10 to the minus 24. What I showed you a few slides ago was only just below 10 to the minus 23. So we've got maybe a factor 2 to go at this mid frequencies before we really start hitting the fundamental noise. Okay, this is, I won't say much about LIGO vacuum system. It's not the biggest vacuum system in the world, but it's one of the biggest, let's say. It's certainly been operated for one of the longest times. I think this has been basically not devacuumed for order a decade. So again, this is recent meaning second observational run. So the previous curves I showed you were for the first observational run, which is in 2015-16. This was around about the time of the first signal. O2 was 2017, I guess late 2016 to mid 2017. And okay, sensitivity in O2 is slightly improved at one of the LIGO interferometers, maybe slightly worse at the other. So on average, the sensitivity of the 2 LIGO interferometers combined has increased slightly on O2 relative to O1. But of course, it's not just about LIGO. There's operational, there has been Geo 600, which is my local detector, quite close to Hanover. As the name suggests, it's a lot smaller in terms of the arm length than LIGO or Virgo. So it's been used mainly as a prototype or development, let's say, test bed for advanced technologies over the last decade or so. So things like squeezing, this is, well, quantum manipulation of the quantum state of light, which is going to be applied probably in the next LIGO run. Also, the high power laser were developed at Geo. Whoops. Virgo is, let's say, the other European full-size interferometer is 3 kilometer arms. CAGRA is now under construction. It's in fact it's planned to be cryogenic, and it's also built in the side of a mountain in Japan. to mainly reduce the effect of seismic noise. LIGO India is, I think, is now, they've identified a site and they may be starting construction soon. It's basically the LIGO optical components will be taken to a site in India and put in basically a copy of the LIGO observatories. This may happen, well, it should be sometime in the next decade to be operational. Why would you do this? Well, firstly, you get a higher rate of detections in total, but also the fact that you're looking at the same gravitational wave from, let's say, many directions. So each of these interferometers has its arms in a different, oriented in a different way, and so these are different projection of the gravitational wave polarizations. So you're able to better reconstruct what exact gravitational wave signal has come to you. In particular, you can determine the sky location, the distance, and the polarization of the gravitational wave much better with at least three detectors. So, as I said, Advanced Virgo is the third piece of the triangle that we have at the moment. Advanced Virgo, in terms of becoming operational, was just last August that it started observing. So this was during the last month of the LIGO's second observing run. If you look at the sensitivity to binary neutron star mergers, so the average distance at which you're able to detect a binary neutron star merger with a certain signal to noise ratio, this is just a plot for Virgo. You see it's around 0 at, let's say, sometime in May. So I guess last year, Advanced Virgo was not really a detector 1 year ago, but by the end of July last year, it was up to, well, 25 megaparsecs. So that was within a quarter of the range of LIGO's more sensitive detector. So this means at this point it's actually able to do astrophysics. So this all happened within, let's say, within a couple of months. I should also mention, well, Virgo is in Italy, and yeah, this is another aerial picture. Poland is collaborating in Virgo, well, many other European countries. So if this is, let's say, a visual representation, this may have been on the day of detection of, let's say, one of the things in August, maybe the binary neutron star. You can see the lowest curve is LIGO Livingston, just above that LIGO Hanford. The purple curve is Virgo. So now there's a lot of these lines in the spectrum. So these are instrumental effects, probably due to some undamped vibration. So in some sense, this is a symptom that Virgo had been only operating for a few months, and I think in future runs, the spectrum should get a lot smoother. But the fact is, it's within a small factor of the LIGO one. That's the most important. And then GEO is way up here. Well, okay, GEO high frequency sensitivity is comparable to Virgo there, but okay, the fact that it falls, you have essentially no GEO sensitivity below a few hundred hertz, is also correlated with the fact that it's a lot shorter in terms of the arms. So I'm sure people will all remember this, the first gravitational wave detection, or at least the announcement of it, which is now over 2 years ago. This is what people saw, let's say, within a few minutes of the detection happening. Someone in AEI Hanover got an email or a telephone call, and people said, well, something interesting is happening, we should look at the data. And this is what was seen. So this is a representation of, let's say, excess power, so excess amplitude of fluctuations in the data as a function of time and frequency. So you see something that is rapidly increasing in frequency and then stops. It's worthwhile noticing this detection was made without the use of general relativity at all. So without the use of calculated templates, just some algorithm which detects, well, basically blobs like this, and they don't even have to be going up, they could be any shape. So it's an unmodeled detection. So if we want to use this, for example, for testing general relativity, in some sense, the fact that this is detected is not biased by any prejudice in terms of using templates to make the detection in the first place, if you think that's a prejudice. If you take, this is a time frequency representation of the data. This is rather a complicated algorithm to make this. If you just take the strain data as a function of time and you use very standard, let's say, even audio processing techniques. So if you go to your hi-fi and turn down the bass, the low bass, and you turn down the high treble, and you're just left with the mid-frequencies, this is what it looks like. So it's actually visible to the naked eye. And this is actually very lucky in that it was strong enough that we could do this. Most gravitational wave signals are really not strong enough to be seen by the naked eye. You really need these complicated data processing codes. So, well, what you see is it lasts about 0.1 seconds, and as I said before, the frequency increases over time, the amplitude increases over time, and then it stops. So essentially, okay, there should be sound on this, but I don't think we're getting sound. So yeah, the title of this slide is now kind of redundant, unfortunately. But okay, this shows you at least the relationship between this blob representation and the strain as a function of time. So this matches, in fact, what Professor Jaranowski has already told us about the predictions from general relativity, or at least from people's attempts to calculate within general relativity for black hole mergers. So the gray region here is the range of modeled signals. So I think it's extended one body? Yes. Effective, right. Yeah, what's anyway. Effective one body templates, and this is the range of templates that are compatible with the data, let's say to within 90% confidence. The red plot, the red line is a solution of general relativity provided by numerical relativity for some choice of parameters within this grey region. So, well, this shows you that at least they're consistent with one another. This doesn't necessarily tell you that the data is 100% consistent with the solution of GR, but at least this shows us that the templates are sufficiently accurate as measured by as compared to numerical relativity. So, this so-called template bank, which is what we use for optimal detection of signals that are described by GR for the merger of two compact objects. Now, that has already been mentioned. So, 250,000, that was in the first observing run. Now it's more like 400,000. In order to make the detection with these modeled analyses, we correlate the data with each of these template waveforms. We slide the waveform over time because we don't know at what time the merger is going to occur. We enforce that you see the same template in both detectors within 10 milliseconds of each other, and that the spins and the component spins, component masses be consistent between the detectors. So this is the method which should give you the maximum number of compact binary merger detections if those detections are actually described by GR, so if the templates are accurate. And okay, using this method, and well, some of the detections have been made by unmodeled, just blob detectors, as it were. Some of them have been made with templates. So this is, I guess, now an incomplete summary. So over the 01 and 02 runs reported so far, there have been 5 very high SNR significant detections and one further event which we call LVT because the probability of it being a signal is not very close to 100%. Statistically, it's more like 90% probability of a signal, so we can't absolutely rule out noise as cause of this event. So these have slightly different masses, different durations of the signal, different numbers of cycles, etc. But they all look like binary black holes. Oh, except the binary neutron star, of course, which you've heard about. So the great thing about the binary neutron star is it's not just gravitational waves. So if anyone was considering that, maybe we're just making mistakes all the time with our data analysis or with our understanding of the detector, and what we were seeing was just kind of statistical artifacts, well, then we'd have to explain the fact that we see within a few seconds a gamma ray burst from the same region of the sky, and then within a few hours unique optical counterpart. So one very nice thing you can say from the fact that you get the we don't see actually the merger of the binary neutron star systems in gravitational waves. We can, let's say, visualize or detect the gravitational wave signal up to a few hundred hertz. What Luciano was showing you was the spectrum of gravitational waves up to a few thousand hertz. Unfortunately, the detector's sensitivity is not really sufficient to see this at all. So, well, as I've written, no detectable post-merger DW signal. This ought to change in the next few years. Basically, we're not operating the system with the full amount of power in the detector arms at the moment. So if you just pump up the number of photons in the arms, you may, well, obviously we can't promise anything for what's going to be detected, but it may be possible to see some evidence of the post-merger in the next few years. It's already been mentioned that the binary neutron star component's tidal vulnerability has been bounded above, so this rules out some equations of state just from looking at the gravitational wave signal. Obviously, there's lots more considerations you can put into that. But to come back to the fact that, we see the last few cycles before the merger, let's say, and then a gamma ray burst happens within 2 seconds. You see, you can use this order of magnitude of delay between the two as seen on Earth to put a bound on the difference between the speed of gravity and the speed of light. And this actually already rules out a lot of theories, let's say alternative theories of gravity, which people have tried to put together to have like alternative explanations of dark matter, dark energy even. So this made some cosmologists unhappy and some cosmologists very happy. As eventually, I think there must be hundreds of papers of like alternative theories of gravity and what their effects are on cosmology, and people no longer have to read half of them because they're now ruled out. This is, let's say, a summary of LIGO-Virgo detected binary black holes versus electromagnetically detected black holes. So these are black holes in binaries with normal stars, which are accreting matter from those stars. This is just mass in solar masses. Neutron stars, and then the one binary neutron star. Well, we don't, observationally we don't know what the end point of the neutron star merger was, but okay, something with 2 point something solar masses. Question?
Just a quick one. What was the actual resolution of this binary observation from the gravitational observation? Because you say there was a gamma ray burst and optical counterpart, but with what resolution did the LIGO actually?
That's a good question. So I think the localization on the sky from LIGO plus Virgo is order 30 square degrees.
Yes. Oh.
So, okay, if you look at, this galaxy is, well, I guess less than an arc minute, so, you still need very large field of view telescopes to be tiling this region. I mean, you know, if you consider that the whole sky is tens of thousands of square degrees, the chance that this counterpart happens just by chance within a few hours and also within this small sky region is extremely small. But yeah, it's a good question. Okay, I won't say too much about what this tells us about astrophysics, and I think there'll also be another talk about black hole astrophysics later in the conference. So this is a sort of summary. I don't know if you can see these faint contours, summary of the state of our knowledge a few months ago about binary black hole masses. So component masses start from maybe order 10, they go up to maybe order 40 or 50. So at least these larger masses are large relative to previously known black holes in binary systems. Spin magnitudes, it's actually quite difficult to measure black hole spins. They have, let's say, subdominant effects on gravitational waveforms. It seems that the spin magnitudes are smaller than the maximum spin allowed by GR. So these, for almost all the black holes we've seen, they're very far from being extremal in terms of the spin. So I probably won't say anything about the formation scenario. I mean, we can we have a small amount of astrophysical information from what we've seen at the moment, just from the fact that it's possible to form such systems. Basically, if the black holes are formed by supernovae, so by core collapse, then we know that the progenitor stars should not have lost too much mass by stellar winds, so this puts a limit on the metallicity of the progenitor stars. But apart from that, we really know at the moment very little about the formation channels. So, okay, I get to the main point, I think, for this conference is it really just GR? Is everything that we've seen in this gravitational wave strain, is that compatible with the predictions of general relativity? Or if it isn't, if you have some theory which is not general relativity, what constraints do you need it to satisfy? So there's many ways we can answer this question, because there's an infinite number of ways in which you can have a signal which is not general relativity. So we can't test all possible non-GR signals, because that's an infinite dimensional space. So we think of some ways in which to compare different ways of reconstructing the signal, or compare different ways in which you could deviate from a GR signal. So one thing we can do is to take what's called a wavelet reconstruction of the signal. So that's, I think, this, again, I hope you're able to see something here, this light grey region. This is a reconstruction of a gravitational wave signal from the data, but without assuming anything else except that it's a smooth function of time, and that it's essentially the same signal in both detectors. So it's a statistical reconstruction, so you get, let's say, 90% limit. So I called it model-free. It's not completely model-free, because it has some assumptions, as I said, about the smoothness of the signal, but apart from that, it should be, it's not tuned to reconstruct or detect anything that is specifically like a binary merger. You can compare this with the reconstruction using the binary calculation templates, or you compare it to numeric relativity, and they all lie on top of each other. I mean, this is a visual proof that basically there's not that much room for non-GR. This is not yet a statistical proof. Okay, again. Okay, I don't know if this is going to play. Well, this is just a nice movie to either wake you up or cause you to fall asleep. At this rate, it probably causes you to fall asleep. So you see here is I think, horizons of the two component black holes before they've merged, and then some measure of the gravitational wave amplitude. Well, technically you can't really define the gravitational wave strain or amplitude until you're a long way away from the source. So this is some quantity which will kind of asymptote to it. So and you see how the progress of the simulation. So this is an NL simulation. I was going to say it's not running in real time, but at the moment it seems to have slowed to a complete stop. So who knows?
I really don't understand this movement.
Okay. In what sense?
Well, this is supposed to be a space-time diagram, right? Time is going up, so the wave should be moving on a null cone, not on a flat.
No. This is a slice. This is a equatorial slice.
Yeah, I'm thinking about a trajectory, right? The trajectory. You're putting
okay.
two things together.
Right. So
you're
yes.
having a space-time diagram and.
Right. So this is the Pants diagram, and this. Yeah. Okay. This is somehow abuse of. This is kind of a Hollywood visualization. So in terms of the movement of the event horizons and the eventual merger, this is like a space-time diagram where we're just gradually moving up. But in terms of the waves, this is not a space-time diagram. This is just a slice.
Yeah.
So yeah, well, as I said, this is mainly for entertainment purposes. Okay, so what we can ask is, in a statistical way, can we compare the this template-less or wavelet reconstruction with the template samples? So we don't know exactly the masses and spins of the black holes that produce this, but we can take the results of parameter estimation with the binary template models, and we can see, we can calculate something called the match, which is essentially if you add noise to one of the waveforms, how likely it is that you get the other waveform. So, okay, there's a more technical definition, but you can also think of it as to what extent the two waveforms overlap with each other, given the presence of detector noise. So the gray regions are this wavelet reconstruction. What one can then do is calculate the match of this to the binary modeled reconstruction. So again, that's a statistical calculation. So you could just do that to samples, and each sample will have a different mass and spin. So you can take a median of that, and well, you get a 94% match between these two reconstructions. So okay, you don't get a 100% match because essentially this this wavelet reconstruction, which is unmodeled, it will not be able to pick up all of the signal. So it might miss some of the signal at early times. It might miss some of the signal at late times when the amplitude is smaller. So what can we do with this? Well, we can simulate a lot of signals and calculate the same quantity, recover them with the binary templates, recover them with the wavelet analysis, and calculate the same overlap between them. And what we see is for comparably high mass signals, you get, let's say, matches of order 90, 95, nearly 100%. So the fact that you see nearly the same reconstruction with and without the template models is very typical of, in fact, the signals that we expect to come from GR. So that's one way of testing whether what we see in the data is GR or not. Another way is to take the best fitting template model, so the best fitting GR reconstruction, remove it from the data entirely, and then ask, well, is there anything left? Well, okay, what's going to be left is noise. So is whatever is left pure noise in some sense? Can it be modeled by, the standard model we have of the detector noise is so-called Gaussian noise, then we can let our unmodeled searches loose on this residual, ask whether they find anything. I mean, if you just let a search run on just pure noise, it's not going to find absolutely zero, because still pure noise, because it fluctuates, is consistent with the presence of some signal, but it will be a relatively weak one. So what was found using this unmodeled search on the residual, well, what you get is a 95% upper limit that any remaining signal had SNR less than 7.3. So in some sense, this is a bound on any non-GR signal that could have been also in the data at the same time as the GR modeled one. Okay, and again, what do you do? What can we make of this number 7.3 S upper bound on the SNR? You can run the same analysis on hundreds of chunks of data where you've not made a gravitational wave detection, so you believe it's just pure noise. And this is the distribution of this like residual SNR over hundreds of chunks of just noise data. And you see it runs from 5 point something up to 9 point something, so 7 point something is very typical. So again, we can't completely rule out that there's some non-GR component to the signal, but at least we can say that it's no larger at this time than at any other time, on average. Okay, I won't say much about this last point. What we can also ask is, we like switch to a different sort of question. We have a signal. Are the different parts of the signal mutually consistent in terms of the system that has produced them? So if we go back to this picture, yeah, okay. Inspiral, the beginning of the signal, you can think of this as 2 point masses. Ringdown at the end of the system, you can think of this as one perturbed final state with just a quasi-normal mode. And this is essentially just a damped sinusoid. If something non-GR happened, then maybe the parameters you deduce from this regime and this regime would not be consistent with one another. Let's see what happens if you try and deduce the system parameters just from the first half of the waveform or just from the last few cycles. And this is one of the tests that is done, the so-called IMR consistency test. So there's some nice coordinates for performing this test, which is you can ask what is the final mass of the black hole that is formed by the merger. You can ask what is the final spin of the black hole that is formed. These quantities both depend on the masses and spins of the components. So this is two different ways of measuring the masses and spins of the components, which translate into two different measurements of the final mass and spin. If you just use the early part of the data, so you cut off the data such that you don't see the merger and the ringdown, this is the confidence interval you get. If you just use the second half of the data, so that's an independent measurement, you get a different confidence interval. If you use all of the data at once, you get something in the middle, and you see these all overlap with each other. So at least if there is an effect of deviation from GR, it's not showing up here. You can also try and isolate the last few cycles of the signal. If the signal is sufficiently strong, you can actually see the ringdown. And then there's another set of coordinates you can use for describing the ringdown. So the frequency of the quasi-normal mode and the decay time. The dotted lines are where you just estimate these directly from the data. The black region is where you use not only the data, but a full model of the whole of the signal. So you use all of the data and the assumption that you have a GR binary merger. And okay, there's different ways you can try to isolate the quasi-normal mode. It's never possible to really cleanly isolate it because it's kind of connected to the rest of the signal. But the fact that this lies within this 3 millisecond contour shows you again that there's no visible discrepancy between the prediction of GR for the quasi-normal mode and what was actually seen. So I guess the last type of test we have is, again, it's more dependent on the existence of these templated models. So one particular type of these template models based on GR and numerical relativity is called phenomenological model. So I don't know, IMR phenom is just a name. The way it is constructed is by having an inspiral part, an intermediate part, and a merger ringdown part. So these are defined between different frequencies, gravitational wave frequencies, and these have various parameters that describe them. So in particular, this inspiral part has parameters which are labeled from 0 to 7, which are just the post-Newtonian coefficients, essentially. There is also the merger ringdown part has some parameters which actually also describe the quasi-normal mode frequency and damping time, but in order to connect them, you need a few more fitting parameters. So, the obvious thing to do, this is a model of a waveform, it has many parameters. You could try varying one parameter away from its predicted value in GR or predicted or fitted from NR. You could actually vary several parameters at once and see if you can infer bounds on the deviations of these from GR. So what we see, so we have several of these Pn parameters, which are called phi. There's beta and alpha parameters which deal with the merger and the ringdown. If we vary each of them separately, we get these red, basically violin plot limits. So this shows us, for example, this 0 Pn parameter goes between 0 and minus 0.2. At least the value 0 is within all of the confidence bounds here. So this is no evidence for any deviations of any of these parameters away from the GR value. One nice thing is if you compare this to these to the bounds set by the double pulsar system. So this is a totally different regime. This is a much lower frequency source of gravitational waves. So the 0 Pn parameter of the waveform is bounded more precisely by the double pulsar. All the other Pn type parameters are more constrained by this first gravitational wave detection.
It's not really fair to vary them one by one. Presumably, if
True,
GR breaks
yes.
down, it breaks down across the board.
Right.
So you should allow everything to flow.
Yes. So in fact, these blue bounds are bounds on varying multiple parameters at once, and yeah, as you say, at least for the Inspiral, okay, you can bound the 0 Pn parameter independently of whether you allow other ones to vary. But sorry, the 0.5 Pn parameter. You can bound some of the merger ringdown parameters independently of whether you allow other ones to vary, but these Pn parameters, they're very strongly correlated, so yeah. Well, that was just one gravitational wave. If we now update the bounds, I do not think we have the multiple, yeah. So these are just the single parameter bounds from the most recently published set of gravitational wave observations. So now, if you allow, let's say, the 2 Pn parameter to vary, it will have an effect on, and if this is actually the correct theory, then this will not just have an effect on one gravitational wave observation, it will have an effect on many of them. So you can combine the data, from many binary black hole detections to improve these bounds. But you're right that, and I think, we will be putting out, let's say, bounds on variations of multiple parameters, but also from multiple events. So I think eventually we should be able to put some non-trivial bounds on like varying combinations of Pn parameters. Okay, and then we can also, if we see several high mass black holes, we can also put combined bounds on the deviations of this relation between the initial and the final spin and masses. So we can generalize this IMR consistency test to be applicable to combining several observations. Okay, so I've probably gone through all the time. I should just mention that we're not even halfway through the observational plan for Advanced LIGO and Virgo. So Advanced Virgo has just had 1 month of observing so far. It will take at least 1 more year of operation and then another year or so of upgrade before we really get to the final sensitivity of the advanced network. So, okay, I won't say anything particular about what comes next, but people are already planning what to start spending money on after that, and how to get to this regime where we have tens or hundreds or thousands of detections where we can really do much more precise tests. So, this is the, let's say, this is the headline. So if you're looking for deviations from general relativity predictions, based on the actual signals we've seen, we have no evidence at the moment, but we can say that, okay, so far we have relatively small, low precision, and the precision is certainly going to increase a lot in the future. Anyway, thanks for your attention.
Thanks, Tom, for the comprehensive presentation. Are there any questions?
Yes, yes, of course.
Yes, please.
First of all, I would like to say that, of course, everything is consistent with general relativity. But the question is as follows. Is it consistent also with some alternative theories of gravitation? And the answer is also yes. For example, there is a quite good alternative theory of gravitation designed by John Moffat from Canada, from University of Toronto, and this theory is consistent also. But the masses of black holes, all of these events are consistent, but the masses of black holes are quite smaller than in general relativity. This is the one difference. But generally is consistent. The second thing is more difficult. The second question: is it possible to detect gravitational waves which are not so small as in the linearized theory, but which are describing very strong gravitational field? Because we have exact solutions of Einstein equations. For example, generalized plane waves, which could have a very strong gravitational field. But the problem is such: what are the sources of such gravitational waves? But the solutions can describe very strong gravitational field, not such small as here that you need such detectors, but these fields are really strong.
Wow. So I agree to start with that there are a bunch of alternative theories which have survived. Even a very old non-GR theory, Brand-Sticky theory, has survived all the tests, and there's general types of scalar tensor theories. I don't.
Yes,
okay.
but in the scalar tensor theory, you will have also additional polarization of gravitational wave, which we don't see here.
Okay.
In the case of Moffat theory, there are such not additional.
Okay. Yeah, I mean, the LIGO does not have a favorite non-GR theory. So if you can calculate deviations from the predictions of gravitational predictions of GR for any specific theory, you can compare them with the bounds we have here. Now, okay, strong gravitational waves, and if you just sit like a few kilometers away from a binary black hole, you'll see strong gravitational waves. But I don't think that's going to happen. Yeah, I think it's like astrophysically, you have to ask, what are the possible sources? And the other constraint is the interferometers can only operate within a certain range of gravitational wave strength. So if you put a too strong gravitational wave signal into the interferometers, they're going to break or stop operating. Now, okay, that's not a very strong motivation for building. I guess you could just have an array of like much less sensitive gravitational wave interferometers or detectors, and if the big ones break, you still have the small ones. I'm not sure. I don't know what are the astrophysical systems that could create these, much stronger.
For example, colliding gravitational waves. There is even a book about this solution, colliding gravitational waves.
Yeah, but what causes them to happen close enough to us?
Yeah.
Anyway, Luciano?
Yeah, so it was mostly a comment to your question. I think it's very difficult to exclude things, but maybe there are examples of theories where you can show that these are inconsistent with the data. For instance, if you try to interpret the very first big black hole merger in terms of gravastars, which are a very nice and ingenious solution, you find out that gravastars cannot be used to explain the observation. So there are ways, even with the large uncertainty that we have, to rule out some ideas.
Well, and Alex Nielsen will be talking about yet other ideas or motivations for looking at non-GR signals at the end of the conference. Was there a question?
Yes, Jose. Yes. There's a recent paper by Tom Brockhurst and Smoot and other people claiming that there might be a magnification of the signal into intermediate galaxies or things like that, and that these masses are overestimated. Do you have any comment on that?
So people other than the authors of this paper have also investigated what is the most likely source of scenario under which gravitational waves could be gravitationally lensed by intermediate either galaxies or galaxy clusters. Well, the conclusion that most people come to is that lensing by clusters is much more likely than lensing by individual galaxies, but is still very unlikely for any given signal. So for like several of the signals we've seen to be strongly lensed is exponentially unlikely. And then, we also have, well, let's say, at the time when we published the final results from the O2 observing run, I think we're planning to make some further statement about this claim, but I can't tell you what that is at the moment. But we are certainly aware of it, and we will be commenting on it in a future publication. But intrinsically, I think it has very low prior odds to have occurred.
All right, so thanks, Tom, again.